All right. Well, good afternoon, everyone. Thank you for joining us for today's conservation webinar series as we continue our Beyond the Basics Advanced Cover Crop series today. Back to our original kind of PowerPoint format with this, but we're pleased to have with us Dr. Shalamar Armstrong, Professor of Agronomy and Conservation Cropping Systems at Purdue University, sharing with us some of the research he's been doing on soil nitrate fate, availability. Are all cover crop species created equal? Because that was definitely something that was of curiosity as we explored cover crops in Iowa, is how do these different cover crop species all interact and perform? So we're pleased to have Dr. Armstrong here today. If you have questions, please feel free to put those in the chat and we'll host the Q&A session following Dr. Shalamar's Armstrong's presentation. So with that, I will turn the virtual floor over to you. Thank you so much.
All right. Thank you, Liz, for that introduction. And thank you, Iowa Learning Farms, for this wonderful invitation to kind of share a narrative of our work for over 10 or 15 years in cover crop systems. So I want to start off just, let's see, with this idea of sustainably intensified agriculture. So this is an idea that I've discovered in the literature, and I agree with it. Most farmers want a system that is sustainable, but yet they have to do it in a way that is intensive. So how do you combine those two concepts of sustainability and also being intensified? Well, there are two tenets that this principle holds. And the first is maximize profit and production with the system. So we have to be profitable in the system to be sustainable. Then second, while being productive and profitable, the idea is to minimize environmental damage or to increase ecosystem services within the ecosystem, within the environment. So when you put these two together, you have SIA, sustainably intensified agriculture. Now, one of the best ways to do that is to have cover crops be included in your system. So we're talking about cover crops and nitrogen. And so let's just look at how does cover crops impact or interact with nitrogen on the landscape. So first, cover crops prevent soil erosion. That was the genesis of the use of cover crops. All right. And believe it or not, in surface runoff, you can see this water moving here, surface runoff. This is a picture from central Illinois. There's actually nitrate in that water, right? And one could question whether cover crops are preventing some nitrate loss in surface runoff. Definitely, we know that cover crops can reduce nitrate loss via subsurface drainage. We're going to look at some of that. And then when you have a legume in the system, there's this aspect of nitrogen fixation from the atmosphere symbiotically, right? And then you have to also consider if you're increasing vegetative growth on the landscape, there's some decomposition of that vegetation. And so there could be also gaseous losses that's coming from the vegetation itself. But also, some of that nitrogen, the fate of it is plant uptake, right? Which leads us to number 4. So you could possibly get greater nitrogen use efficiency. Good plant uptake then translates to more competitive yields with cover crops in the system. It does require a bit of management to get that done. Okay, so those are kind of 4 ways that cover crops impact nitrogen cycling. And let's start off with just looking at a long-term study that we are yet conducting in central Illinois, where we have a tile drain system, and we're looking at the impact of cover crops on the landscape coupled with nitrogen management to understand the coupled impact. And you can see here to the left, we have 3 replications of 5 different treatments. And basically, we'll be showing you the results over a 10-year period, 6 corn years, 4 soybean years in this tile drain system. So this is a long-term system, corn and soybean rotation, and dominantly there's strip till before corn and then there's no till before soybean. We're able to tap into the subsurface drainage through automated water sampling that's powered by a solar panel, which gives us the consequence or quantifies nitrate loss depending on what the surface management is. And so what we found in the 6 corn years of the 10-year study, when we looked at flow-weighted nitrate concentration, found a 39% reduction in the flow-weighted nitrate concentration where we had the presence of cover crops. And this is a cereal dominated mix. It was cereal radish, and then we went to purely cereal on the landscape. In the soybean year, you have a lower overall flow-weighted nitrate concentration, but yet the presence of cover crop did matter because we had a 32% reduction in nitrate, in flow-weighted nitrate concentration. Okay. And so when you think about the load, right, and this is cumulative load or nitrate loss over time, we saw from 2014 to uh, 23, we saw a 42% reduction in nitrate. So how is that happening? The cover crop is growing on the landscape, is absorbing or taking up nitrogen that's available in soil solution, whether that's residual nitrogen from the previous year fertilizer that didn't get absorbed by the cash crop, whether that could also be mineralized nitrogen if you have a high organic matter soil. You see that gray line that represents the no cover crop control, where we added no cover crop and no nitrogen, so zero control actually. And we still getting equal loss relative to when we added 200 pounds of nitrogen to the system. And so that's because we have high mineralization and we have a high organic matter soil, about on average 3.5% organic matter. But when we added cover crops to the system, we got a 42% reduction over time. Okay. So 2 of the years, 2017, 2018, we actually looked at the gaseous losses, and we found significant reductions where we had this cereal dominated mixture. Okay. Um, and one of the things I wanted to point out is like, how is nitrogen lost in the system? Is it more nitrate loss than N2O loss? Well, clearly in these 2 years in this tile drain system in central Illinois, we found significantly more nitrate loss relative to N2O. Okay, but when you average both years, we found a reduction, over 50% reduction in nitrate loss or total inorganic N loss from the system with cover crops. So all that I've shown thus far has been primarily on a plot scale, let's say less than 2 acres, right? And so here is another study that is also long term, and I'm just showing a glimpse of the data here, where we are in central Illinois with a paired watershed study, where one watershed is about um, 770 acres, and the other watershed is about double that size. And so we cover cropped half of the larger watershed, about 49% of the larger watershed, and monitored the water quality to see if we can see a signal. And what we found was that when we first started out, there was a small signal in reduction in flow-weighted nitrate concentrations on the landscape, where you see the green cover crop. The green dots represent the cover crop watershed, and the black dots representing the control where there was no cover crop. And over time, and cumulative effect, we saw that signal became much stronger on a watershed on a watershed scale, where we only are cover cropping 50% of that watershed, right? And so that was neat to see that we're seeing reductions on a plot scale, and then that translated to reductions on a watershed scale where we have a lack of control, right? On a plot scale, we control all of the aspects of management, but on a watershed scale, we're visitors. And basically, the only thing that we're controlling is that we're flying on cover crops with an airplane, and then we're monitoring their growth over time. So we saw reductions in both cases. All right, so environmentally, cover crops on the landscape is doing a good job reducing nitrate loss, reducing N2O losses in that particular setting, those particular years. But then when we look at what's the agronomic impact of having cover crop inclusion, right, in the corn and soybean rotation, no impact, no effect on soybean yield, but yet there is we found about a 6.9% reduction in the six corn years. And we dug a little deeper and we took some intensive plant sampling, and we found that about 60 to 75 days after cereal termination, which is on average is about V12, we saw the difference, a differential, if you will, in nitrate uptake occurring. That by the time you get to R6, when that plant is kind of shutting off, we see a delta of about a change or a differential of about 60 pounds per acre, right? Where a reduction in nitrogen uptake for corn in cover crop residue relative to corn in the non-cover crop control. That then translates into lower yield. Okay. And so we begin to kind of dig in to try to understand what's the impact of that. You know, what's the mechanism? What is actually happening? So we basically used 15N, and we were able to track. This is traceable nitrogen that we introduced to the landscape in this field study, and we introduced that to the cereali, and we terminated the cereali as normal. And within the residue of the cereali, we planted corn, and then we tracked the uptake of cereali into the corn over time as the corn developed, right, all the way to harvest. And here's what we found. We did that for soybean, and we did that for corn, two different locations, Indiana and Illinois, in one year, 2018. And we found that basically we could expect, let's say on average, 10% of the cereal nitrogen that's in the residue to be used by the next corn crop, or even by the next soybean crop or the subsequent soybean crop, right? So this is evidence that cereal is very stingy. It's not giving it back. It's not giving back a lot of its, a large portion of its nitrogen that it takes up. So we decided to say, okay, that's in the field, and we did a more detailed job with Roth et al. Um, in the lab, and basically we are quantifying the release of cereal residue nitrogen within four different soil pools: the inorganic soil pool, the organic, the soil microbial, biomass nitrogen, and then what we're calling unrecovered. And basically, over 120 days after termination, assimilated termination of the cereal, we see that 89% of the nitrogen within the residue is unavailable, right? And so that kind of speaks to that exactly what we found in the field. So we confirmed this in the lab. And so we have to consider this, right? Um, this is a cartoon that I created to try to help people understand the dynamics of nitrogen when you add a cereal dominated mix to the landscape, right? And so with this first bar, this is kind of representing with no cereal on the landscape, where 72% of your nitrogen remains in the soil. But because you don't have the cover crop to absorb some of the free and available nitrogen in the system, in the soil solution, you're getting 28%, 28% reduction or loss of nitrogen via tile drainage. So if it's below the line, it's lost, right? And so when you add cover crops to the system, the theory is that the cover crop then absorbs some of the nitrogen that is susceptible for being lost, right, within the system, within itself. So it takes up nitrogen within itself. We call that nitrogen uptake, about 51%. And in doing so, you reduce what's lost via tile drainage. right? And so one thought was that, hey, by the time we plant, that a large portion of this green would be converted back to brown, available for our corn to use in order to grow. But what we found actually is that CRI is very stingy, and it leaves us with a large portion of the nitrogen that's within itself, within its structure, within its residue, not available for the subsequent corn, resulting in a 40 to 60 pound adaptive management challenge. So this is nitrogen that would normally be there that's not there because the CRI did its job, right? And when you think about it, you're going to find that 40 pounds is very similar to average nitrogen uptake from all of the study over past years that we've found. And you're going to see that as we progress through the slide set. So we needed to come up with some strategy. That has been kind of the drive of my group to how do we reduce the cash crop yield lag when planting behind a cover crop. And so one of the things that we start studying is precision planted cover crops. So let's plant in a way where we can reduce the antagonistic relationship between the cover crop and the cash crop. Okay. The other thought is, can we manipulate our cropping system to include overwintering legumes? And so we know that legumes can fix nitrogen symbiotically from the atmosphere and possibly use some of that nitrogen as a nitrogen credit, reduce input costs, right? And legumes are not strong scavengers, and so they would kind of leave the nitrogen, mineralized nitrogen or residual nitrogen in the system in a way that's more comparable to the non-cover crop control, thus reducing immobilization of nitrogen. And so we got a grant from North Central SARE, which then propelled us to look at several iterations of a study similar to this, where we have factors of cover crop species, right? Balanza clover was the legume versus the conventional um, cereal, which is the most commonly used or adopted cover crop in the landscape. I'm sure that's the case for Iowa also. Then we looked at another factor, planting method, whether conventional or precision. And I'll talk about that in a second. And then we looked at seeding rate, right? Whether we do a full or reduced seeding rate. So when you think about precision planted cover crops, we're talking about planting cover crops in strips across the field on 30-inch centers, right? And then leaving 30-inch centers as a skip row for the corn to be planted. There are a couple reasons why we think this is important, why we want to test this. The first is we can simply cover, can we get the same biomass with 50% less seed because we're covering about 40 to 50% less area across the field? Okay. Secondly, if we are leaving a skip row, possibly we're reducing the interaction of the cover crop growing in the zone where the cash crop will be planted, where the corn will be planted. So maybe we're reducing water use in that zone. Maybe we're reducing nitrogen immobilization in that zone to possibly ease the competition between the cash crop and the cover crop and alleviate some of the yield lag that way. If you are sowing less seed per acre, you're also reducing your input costs. And so that was another factor that we wanted to kind of examine. How much CRI do you really need? How much cover crop do you really need to get the job done, right? Could you go with 50% less with a precision planted and yield about the same performance on the landscape? So here's just some field shots of what it looks like. So you see the precision cereal, and we managed that cereal. Um, we didn't want biomass over 2,000 pounds per acre because things get really tough for corn as you exceed that. This is conventional planted Balanza clover. You can see here. Um, and then this is what it looks like when everything is terminated, of course, right? And so you can see very brittle, brown, um, some green showing up here, but it's pretty well turned and terminate it, right? And so that's when we want to plant. So let's look at cover crop performance, and this is over a 5-year period. Okay, it's the averaged over a 5-year period. So first of all, I want to just point out that there was no difference in well, there was difference with planting method. Let's start off with cerealized. So precision planted basically outperformed conventional planting. We think that's because of you have the spacing, which allows more sunlight to hit more of the cereal plant. Even though they're less, they grow more vigorously due to less competition due to the arrangement, orientation, and spacing of the planting. Okay, so even this is not that much different, but significantly different, statistically different. But in the field, this will be kind of being about the same performance. When you look at Balanza clover, the opposite occurred. Conventional planted Balanza outperformed as far as biomass the precision. Okay, but on average, your Balanza clover was about let's say 2,400 pounds per acre, where your cereal was about 1,600 pounds per acre of biomass. Of course, we controlled the cereal. We let the Balanza clover grow as long as we could before it was time to plant because we were trying to capitalize on the fixation of nitrogen. So when we look at carbon, so when you get that biomass, the first thing that you get, 40% of that biomass is carbon. So on average, about 937 pounds per acre of carbon, right, accumulated in the biomass photosynthetically by Balanza clover, and about close to 670 pounds per acre for cereal. Of course, we control it, but one of the neat things to look at here is that you're getting the same performance, but with 50% less seed. Okay. And so it is paying off that the precision is paying off in that way already by just looking at the cover crop performance. So nitrogen. So what's happening with the nitrogen? Okay. We're getting about 74 pounds per acre on average. So that ranges from, across the 5 years upwards to about 118 pounds per acre of nitrogen in the biomass, right? For the Balanza clover, that's dominantly being fixed from the atmosphere. For the cereal, about 40 pounds per acre, which is what we saw in previous studies, right? And this is the average about, terminated before the boost stage. Cereal on the landscape. Okay. And so the question is how much of that nitrogen in the Balanza clover would contribute or convert to a nitrogen credit where we can get possibly optimum yield with lower inputs of nitrogen fertilizer. And that's dominantly dependent upon what we call the CNN ratio, carbon to nitrogen ratio within the biomass. The lower that number, the faster or the quicker or the rate of the decomposition of the residue is higher, right? Greater. And so we saw on average across the 5 years, Balanza clover was at about 13 as it pertains to the CNN ratio, and cereal was at about 19. So cereal is projected to, based on these data, cereal is projected to decompose slower relative to Balanza clover, and that's the conventional thought. So here's the first yield slide, and I'm just going to explain this. So we have corn grain yield on the vertical axis, right? And then we have nitrogen added in kilograms per hectare on the horizontal. And this line represents the optimum yield. And so what we see here is that we're getting optimum yield with the cereal, but it's causing us to add 38 pounds per acre more nitrogen fertilizer to achieve that optimum yield. Okay, so we're going in the wrong direction, right? Especially in this climate, we don't want to have to add more nitrogen to get to the optimum yield in the field relative to the no cover crop control. But what happens why is this happening? Well, possibly there is definitely nitrogen immobilization, right? There is a lack of nitrogen available for the corn plant when it reaches its peak nitrogen uptake. And so the uptake is outpacing the ability of the soil system to provide nitrogen. And so you're getting a reduction in uptake, which then relates to a reduction in yield. So when you add back about the same amount of nitrogen that was taken up by the cereal on average, which was 40 pounds, and you need about 38 pounds or 40 pounds to add back to get the optimum yield, right? But now, when you consider Balanza clover, right, which is a legume, we go in the we go in a green direction instead of a red direction, right? And so we get to optimum yield across the field with about 31 pounds per acre of nitrogen less relative to the no cover crop control. And watch this, 70 pounds less relative to the if you had cereal right before corn. So just that simple um, decision to plant a clover before corn relative to cereal rye is causing a significant difference in the input cost to get to optimum yield. So this is showing good potential that if we can get the clover to grow in the environment, that we have the potential to leverage the fixation of nitrogen towards a nitrogen credit. Okay. So I wanted to go just a step further and kind of show across treatments um, the environmental optimum nitrogen rate, okay? The EONR. And so why is that important? So this is the rate of nitrogen needed to get to the yield where you are not um, exceeding a nitrogen rate that would cause damage to the environment through nitrate leaching or possibly through gaseous loss of nitrogen. And so when you compare the Balanza clover, whether conventional or precision had a slight reduction in that rate, so a lower rate to get to optimum yield. Okay. And one of the things in Iowa, I know you use a lot of cereal rye, so do we in Indiana and also in Illinois, right? And we wanted to know if I precision planted that cereal rye relative to conventional planting, do I make a difference in the performance of the crop or the amount of nitrogen needed to get to the optimum yield? And certainly over 5 years, we found that, right? About a 13 pounds per acre of nitrogen reduction in the amount of nitrogen you needed to get the optimum yield when you precision plant relative to conventional planting, right? And we think from the literature, I mean, from the data set and also from literature that we're getting greater in uptake, right? Greater nutrient nitrogen use efficiency. So less nitrogen is needed in order to get optimum yield, less competition for water in the place where you plant the corn seed, right? And so all of those synergies or converging to get a reduction in nitrogen needed in order to get to optimum yield. And because it's precision planted, you're also reducing the amount of input costs because you are cutting your seed rate in half, right? So seed rate normally about 40 to 45 pounds per acre. You can get away with half, get the same biomass, and then get better corn performance because you're reducing the antagonistic relationship between a heavy carbon residue and corn growth, right? So when you plant Balanza clover relative to cereal rye, you're getting a reduction of about 60 pounds per acre of nitrogen needed to get to the optimum environmentally optimum nitrogen rate, right? Which was significant, right? And you kind of expect it. Okay. But what was not expected is just the different way that we plant cereal rye that would cause a reduction in nitrogen needed or better plant nutrient nitrogen use efficiency. That was neat to see over a 5 year period. All right. So there are some environmental trade-offs that we need to consider also, right? some key trade-offs. So we thought about nitrogen uptake by the cover crop, nitrogen uptake in corn and yield, right? That's impacted by the cereal rye as far as corn growth and development. But what about gaseous loss when you add cover crops to your system? Does it occur? The answer is yes, it does. It does occur. And so what you're seeing here is N2O loss in kilograms per hectare, right? This darker color is when there was this is the zero control. So Bonanza clover system, right? We're averaging this over 2 years. Where we have Bonanza clover with no nitrogen added here, cereal rye no nitrogen added, and so forth with the no cover control. You can see just slight increase in nitrogen loss, right? But all under about six, let's say six, so that'll be about 4.5 pounds per acre on an annual basis, like per year, right? But when you add 200, close to 200 pounds per acre of nitrogen to the system, you get it, that nitrogen added, that inorganic nitrogen fertilizer added, really impacts the nitrogen loss as far as N2O in the system, right? Despite the system. There's more loss where you have cover crops, and the two cover crops are similar to one another. And if you look at the differential between the non-cover crop losses when you had fertilization with nitrogen versus when you had cover crops, the cover crops are accounting for about 7 pounds per acre of N2O loss annually, right? But no difference between the two. So really, the story here is that when you're adding upwards to about 200 pounds per acre of nitrogen to the system, along with the new vegetation, new carbon added from the cover crops, you get a combination that could lead to more losses. But when we do, we're still teasing out the whole nitrogen balance. So far, we found that you'll get a nitrogen credit to your system with Bonanza clover, not considering what's lost through tile versus when you have cereal rye, you get a nitrogen deficit because you're having to add more nitrogen to get to the same optimum yield across the field. So real quick, we're going to go through some key management considerations, right? Because you see this system, a lot of the work that I showed you was in southern Indiana, right? So we had a lot of heat units, right? So we can get that clover to grow. But what were some things that we had to consider? So the first was soybean maturity, right? So we want to be able to get clover in, even if you're doing an aerial seeding, you need to try to get it in as early as possible to get growth, or some people can get it in behind wheat, right? But if you come in a corn and soybean rotation type system, you need to try to get early maturing soybeans. And we did a test of 5 maturities across 5 replications in southern Indiana, and we found that there was basically no difference in yield. So that gave us some confidence in the system to come to plant this early maturing soybean, which gives us windows and growing degree days to get the clover to try to take on the landscape. Another thing is you can get the clover to grow, but then you have to, at the end, before you go into your cash crop growing season, you got to manage that clover residue properly, or else you won't see the benefit that you're looking for. So we have two systems here, right? One on the left is planting green. This is our first year. We were green. We were planting green. Okay. And you can probably see a lot of problems, seed to soil contact. We had voles, we had stink bugs. All of those things occurred in that first year, right? Of including Bonanza clover within a corn and soybean rotation. Even though we had those problems, our yield was equal to the control, the non-cover crop control, right? Now, on the right-hand side is when we allowed for over 20 days of decomp to occur before we planted. And we saw significant impacts and nitrogen credits in when we planted brown green versus when we planted green. So managing the residue is really important. You can get the fixation, but you have to manage it to actually make it useful. This is what it looks like when we planted green in 21. This is that harvest, and you can see how much cover crop biomass is still left in the field. So if I could do that, pick that carpet up with my hand, that means that some of that nitrogen has not been decomposed, still in the organic state and unavailable to that crop, right, for that whole growing season. So if you manage that residue properly, you shouldn't see that much there, and more of it should be have a high. The corn should have a higher use for the nitrogen in the clover residue. This is another shot where we kind of quantified, right, climate smart practice, right? This is we had a drought in the vegetative growth period of 2023. We have conventional planted, drilled, and then precision planted, right? And you can see this is not Photoshop. This is on the same day. You can see the difference in the development of the corn where we had that skip row, where we had no competition and probably less water use, where the corn seed was planted with the precision versus conventional. And that was about a 15 to 20 bushel per acre yield difference between these treatments. That was the result of just how we planted the cover crops, and it turned out that way that year. So in summary, then we'll address any questions. When you have a seed rod dominated mixture across the landscape, you can expect to get nitrate loss reductions, right? 30 to 49%. This is on a field or watershed scale. The inclusion of winter hardy legumes, right, before corn planting, you have the potential to get optimum yield with lower fertilizer inputs, right? We saw that over a 5-year period, but this is in southern Indiana. And so as we go north, you have to be more creative. You might have to bring wheat into the rotation, right, to get that stand to be as effective towards a nitrogen credit. Precision planted cover crops reduce adoption costs because you're planting less seed, but had the same performance and reduce resource competition for the corn that's following, right? That you plant in the residue. That was significant. That was something that I believe that was a strong trend across all 5 years and cover crop, across cover crop species, but more strongly, we saw this in when you have precision planted versus conventional planted seed rye. There's also, and we're still working on this, there could be, there are trade-offs environmentally when you add cover crops to the system. You're adding more residue to the system. You're adding more carbon to the system. You're adding more nitrogen to the system. So we haven't tapped into how does Balanza clover affect leaching of nitrogen, right? And we are writing grants for that so that we can put the whole system together and hopefully come back and present a complete nitrogen budget and balance that you may see how the inclusion of cover crops such as legumes or cereal affect your whole nitrogen budget over time. So with that, I want to say thank you, and I'm ready to address any questions. I saw that there were a lot. That's good.
Yeah, if you want to go ahead and go to those next slides as folks get the rest of their questions in. I want to thank our key partners in hosting this conservation webinar series. They include our Iowa Department of Agriculture and Land Stewardship, our Iowa Department of Natural Resources, the Iowa Nutrient Research Center, and the Leopold Center for Sustainable Agriculture. We appreciate their continued support to provide these weekly webinars. If you want to go ahead to the next one. Folks tuned in today to earn a CCA CEU, please be sure that you're emailing Alena Whitaker at alenaw@iastate.edu by 5 o'clock today. Be sure you include your name, the name you used to watch the webinar if it's different than your registered name with the CCA organization, and then that number that we would get your credit submitted on your behalf. So thank you again for those of you that do that. If you want to go ahead to the next one, we've got another survey here. As a USDA funded organization, we do have this voluntary survey that folks can fill out by either visiting iowalearningfarms.org/survey or giving that QR code on the screen a quick scan. It's a very brief survey. If you've already done it for 2026, thank you. You do not need to submit a second one. So yeah, please feel free to fill that out if you have not done so. All right, and then I believe it's next week's webinar. We're going to switch gears a little bit. We're going to talk about corn cobs for improving nitrate removal in bioreactors. We've got department graduate student recently defended her PhD, Taylor Vroman, going to be discussing her research on corn cobs in bioreactors. And then our last slide, as always, our webinars are recorded, and you can find this one as well as all of our advanced cover crops and regular scheduled webinars either on our website, that's iowalearningfarms.org/webinars, or we've also set up a YouTube channel where you can view webinars either by year or topic by playlist. So with that, we will switch over to some questions. I'm going to group a couple of these together because there are some questions about maybe stage of the rye at termination. So, like when you're terminating it, how tall it was, and how you came up with that 19 to 1 carbon to nitrogen. I think they're all kind of interconnected there in terms of how you
Yeah,
came up with that.
yeah. So for the most part, our termination was before elongation, before the boot stage. So kind of aggressive. Um, Previous studies shows that if you allow it to go beyond that stage, then that's when the plant switches over to a reproductive growth stage, and that's when the carbon begin to really exceed the nitrogen, and your CDN ratio shoots up, right? And so we were terminating aggressively because we wanted to get at least 2 weeks window between termination and planting. And thus we got a lower CNA ratio. But even across all of my work with Siri, even at 15 to 19 to 20 to 1 CDN ratio, you still get immobilization. We still measure immobilization of nitrogen.
So there's a couple questions kind of back to your initial just cereal rye work where you're looking at plot scale and then watershed scale.
Yeah.
Um, so can you remind us what the reduction of your nitrogen loading was at the watershed scale? You noted about
Uh,
42% at the plot scale.
yeah. At the plot scale, about 42% over a 10-year period, and we're looking at about at least 30 to 32% reduction at the watershed scale.
Okay. And then how were you measuring at the watershed scale? Was it composite
So
edge of field or how was that
this
being
is
done?
this is edge of field before it enters into conversion into a stream or
Okay.
creek, right? We have automated samplers at the main that is converging in that pours or converges into a creek. We have the tile. We confirmed that that main was servicing the watershed area from tile maps and so forth from the farmers and also from soil and water conservation, really helping us out when we designed and delineated the watershed. So edge of field measurements.
And for that for your plot scale, you were drilling, correct? But then at this
Yes,
watershed scale, you were helping coordinate flown
we were
on. Did you do
right.
any comparison of like the coverage, your biomass or other ways of measuring kind of effectiveness of coverage between those
Yeah,
systems?
yeah. So when we're drilling on a plot scale, we generally have more biomass and it's less variability in the biomass. When we're flying it on over several hundred acres,
Mhm.
we have higher variability and on average lower biomass. However, we have found very low biomass and still good nitrogen loss reduction, right, on both the plot and the watershed scale, because I think that there's a residual effect of adding carbon to the system, which then couples with nitrogen in the microbiome that makes that nitrogen less available. It also increases water holding capacity. We saw reductions in volume at both plot
Mm.
and watershed scale when we had cover crops present versus when we did not, right? So that's also contributing to the load because load is concentration times discharge, right?
Right. So kind of going back to looking at, corn yield impacts, there's a question here about the nitrogen timing. When was
hmm
nitrogen applied in those plots or those
So,
trials?
nitrogen was applied at starter and then at side dress.
Okay.
Yeah,
So not fall. This is all either at planting or after.
correct.
Okay.
It on the latter study where we had the Bonanza clover and the precision planted.
Okay.
In the Illinois study, we started off having cover crops like a cereal dominated cover crops um, in interaction with fall versus spring applied nitrogen, right? And what we saw there was very interesting, is that despite when the nitrogen was applied, um, the cereal significantly reduced nitrate loss by 30 to 40%. So even fall applied nitrogen
Okay.
had a lower loss of nitrate due to the presence of the cereal relative to when cereal was not present.
Were you able to tease out how much of the nitrogen uptake but in the Balanza clover itself was residual soil nitrogen and how much was fixed?
No, we're actually seeking funding for that right now, where we can use M15 to determine how much is fixed, and how much is not. So we haven't teased that out
Okay.
yet. But what we did note is about 32 or so percent of what was in the structure of the Bonanza Clover, what it took up in above ground biomass, actually was used as a credit
Mm.
for the corn. So we do have that conversion, but we do not know how much of the nitrogen within the structure of the Bonanza clover came from fixation versus uh, absorption from or uptake from the soil.
And kind of sticking with this Balanza clover, just some kind of details on how and when it was seeded. You noted that you're in southern Indiana, so
Yeah,
that was one of the aspects, and then at what rate you were doing that seeding.
yeah. So as far as timing, we were trying to get it on prior to September 15th, right? Which could be hard in certain parts of Iowa, right? That's why I was thinking probably coming behind wheat would be a better system, right? Um, Rate. So we were looking at about 8 pounds to the acre
Okay.
in rate initially. Then we do precision, we cut that in half, right, to 4 pounds per acre.
And then what were you using to terminate the Balanza clover? And then you came in and no-tilled that corn as your video showed, but what were you using to
Yeah,
terminate it?
glyphosate and 2,4-D
Okay.
mixture.
And you found that a single pass was enough to make that happen?
We did,
Okay.
we did, yeah. Again, you got good heat units in the
Mm,
south. You got good sunlight in the south. So in the southern part of the Corn Belt, and so where you're more cloudy, um, less sunlight, less heat units, you might have to make adjustments. You will have to make adjustments, but it's not difficult to kill.
okay.
We thought we had crimped it. Really, in the first year, we ended up terminating. We planted green and terminated a week after planting because we thought we had killed it because we thought we crimped it, right, with the planting. And then all of a sudden, like Freddy Krueger started coming back, right? And then it was like, let's get out there and terminate it. Yeah.
So there's a question here, maybe just your thoughts on the potential to tailor cover crop biomass production to avoid yield drag. It sounds like that's kind of what you're doing with the cereal rye.
hmm
Is there a
Yeah.
place we can optimize nitrogen leaching reduction and not see a yield drag in corn?
We have been experimenting with that on tile drainage. And I think what our data is illustrating is that with cereal, we can get down to once you go below 25% of the, like, let's say NRCS, let's say 45 pounds per acre, you go 20 lower than 25% of that, then your nitrate loss is equal to the non-cover crop control, right? Um, and you still have to manage not to have yield reduction, but you have less.
Yeah, and I would think your precision planting also ties in with earlier in the series we had Dr. Allison Robertson, who's a plant pathologist. And so she's focused on the disease aspect, and in her
Right?
research that it's not the spacing also helps minimize that potential
Right.
impact as
We,
well.
yeah, yeah, yes.
So not only the nitrogen aspect, but the disease aspect. So it looks like the spacing is kind of one of the ways we can,
Yeah.
especially for rye ahead of corn.
Correct. And what else we've found? We're finding something else that I didn't show. When you add 20 pounds of sulfur, we've seen over 10 bushel increase in corn um, that's planted into cereal residue. So just like nitrogen is immobilized, it has the same biological fate or track relative to sulfur and phosphorus. So when you add sulfur to the system, you are probably addressing a temporary deficiency that's there, through immobilization, just like you do when we add starter nitrogen.
Um, trying to So there's a couple questions maybe dealing with remote sensing or precision
Mhm.
agriculture
Yeah.
to help with monitoring that nitrogen mineralization. Have you interacted with any folks that are looking into that just yet?
Yeah. Yeah. We actually, myself and Dan Quinn, who's our corn agronomist for the state, we actually have a student between us where we're looking at using remote sensing to create a biomass map to predict nitrogen in the biomass. So biomass and nitrogen in the biomass, right? Then we are trying to use that map to inform a variable rate nitrogen map to try to put back
Mm.
what the cover crop has absorbed that we know it's not going to give back. So Richard Roth, which is a professor that at Iowa State, did the initial groundbreaking work for that, the foundational work, published that, and then a new student came along to try to take it to the next level to test whether we can use our predicted maps to as an input to inform variable rate nitrogen, and now we're going to do sulfur across the field to impact corn yield.
Okay. I'll do a couple more questions. I know I'm probably not going to get to them all, but if folks um, visit your page at Purdue, I'm sure they can find links
Oh,
to all
certainly.
these papers and other things to kind of dive deeper into some of them. But
Yes.
one of the questions here was how long had cover crops been used on these sites? Was it long-term use or short-term use?
So on all of my sites, I think I was the first to use cover crops on those sites, but these were long-term studies. Like the first study is now going on 11 years
Okay.
at the same field, and then the second study in southern Indiana, we're rotating between two fields, and we're going on the sixth year of
Okay.
that study.
And then kind of again, maybe this is next stage in search of funding, but looking at a mix of the cereal rye and clover.
Mhm.
Have you
Yeah.
done any on that?
Yes. So, as a rule of thumb, I found that if I study a single cover crop first and understand its properties, its behavior and performance, then I can go to mixing. So now we're at the mixing stage, right? And what we found in the past, where we have mixed at least two or three species, is that if you be above a certain threshold of cereal within the mix will behave like cereal.
Mm.
So you have to kind of suppress cereal, or else you just have cereal, no matter what your mix is. It'll shade out the clover, it'll outcompete, the oats or whatever. So you just have to control the cereal in your mix. But
Excellent.
we're looking at that.
Well, we'll maybe invite you back when you got a couple years on that to follow up on
Yeah,
this good discussion here. So,
yeah, for
thank
sure.
you so much, Dr. Armstrong. This has been a great presentation. Again, it's
Thank
recorded,
you.
so folks can find it on our website later this afternoon. You can dive back into some of it or share it with folks. But again, thank you so much. I'll give you the
Yeah.
final word.
Yeah, I thank you for the invitation, Liz, and you all are doing a great thing. I'm sure a lot of people are learning, and if you have questions, the QR code still being shared, or you could just simply Google Shalamar Armstrong and reach out. I'll be happy to address those. Thank you so much for the opportunity.
Our pleasure. Thank you.
All right.